types of waves. Now we studied about sound waves, which are consisting of compressions and rarefactions. And these waves are called longitudinal waves. So the sound waves in air are called longitudinal waves. There is another type of waves which we also mentioned, electromagnetic waves, which are transverse waves. So these transverse waves travel in solids and liquids but not in air, whereas sound waves travel in all the material media, which is solids, liquids and gases. So sound waves in air is called longitudinal waves. So let us see the different criteria for these type of waves: longitudinal wave and transverse wave. So we said longitudinal waves are sound waves in air, whereas transverse waves are electromagnetic waves which travel in solids and liquids. So the sound waves in air, which are called longitudinal waves, we have studied about them. The particles of the medium vibrate back and forth in the same direction in which the wave travels. So we have studied about the compressions and rarefactions that are created by the particles of the medium, but the particles as such do not travel, but they just vibrate back and forth, creating high density and low density or high pressure and low pressure regions. And that is how the sound waves propagate. So basically, particles of the medium vibrate back and forth in the same direction in which the wave travels. Whereas in transverse waves, what happens is the particles of the medium vibrate up and down at right angles to the direction in which the wave is moving. So it is very different. In longitudinal wave, it travels in the same direction because particles move back and forth. Whereas in the transverse wave, the particles move up and down, hence they travel at right angles to the direction of motion. So if you take this figure, so this region where the particles are very close to each other is compression region, and where it is far away, rarefaction region, again compression and again rarefaction. So this compression regions are high pressure. It's called high pressure region or high density region because the particles are closer to each other and the density is higher. Whereas in the rarefaction region, this is called low pressure or low density region because the particles are spaced out. So longitudinal wave basically consists of compressions and rarefactions traveling through a medium. So we can define longitudinal waves as the ones which consists of compression and rarefactions. So the longitudinal waves consist of compressions and rarefactions traveling through medium. Now what about transverse waves? See, the transverse waves, let us take, if we represent it in a simpler form, let's say P and Q. PQ is the direction of the wave and the particles vibrate up and down. So this is how the particles vibrate. So they are at right angles to the direction of motion. So let's take, for example, water waves. Water waves in a pond. So how are the water waves formed on the surface of a pond? Let us say XY is the line on which the waves are, surface of the water pond on which the waves are formed. We'll call each peak as A, B, C, D, and in this A and C are called crests and B and D are called trough. basically this is all. In fact, this is the water pond, so below is full of water. Now what is crest? Crest is that part of a transverse wave which is above the line of zero disturbance. See, the XY is called a line of zero disturbance of the medium. See, water is the medium here and XY is the line of zero disturbance because above which the waves are there and below which the waves are there. So XY is called a zero disturbance line. So this is a zero disturbance line, XY. And the A and C are the crests because A and C is a part of the transverse wave which is above the line of zero disturbance. And B and D is the trough which is part of the transverse wave which is below the zero disturbance line. So these crests are also called elevation or humps and troughs are also called as depressions or hollows. So the transverse wave consists of crests and troughs. So the transverse waves consist of crests and troughs, whereas longitudinal waves consist of compressions and rarefactions. So the graphical representation for this longitudinal and transverse waves, let us understand. Because whenever these waves are traveling through the media, we know that some property of this medium changes. Properties like density or displacement. So, in the longitudinal wave, basically what changes is the density. We know in the compression it's higher density and in the rarefaction it is a lower density. So, we can do a graphical representation for a longitudinal wave with density and distance as the parameters. So if we take x and y and then draw a wave, now A and C are compressions and B and D are rarefactions, and this is the distance from the source. X and y towards y is x-axis is distance from source. The y-axis is the density. XY is the line of zero disturbance. And if we plot the horizontal and vertical axis with the distance from source and density, then we get a longitudinal wave graphical representation. So this is basically density of the air. In this case, if the medium is air, and longitudinal wave is basically sound waves or air in the air. So the density of air changes continuously because in the compression time it is high and in the rarefaction time it is low. So the density of this air keeps changing continuously. So we can take that as a parameter for representing longitudinal wave. So this is basically a density versus distance from source. This is the longitudinal wave representation. And what is transverse wave representation? So if we take transverse wave, for example, if xy is the line of zero disturbance, what changes here? Here in the transverse wave, the particles move up and down. So it is a displacement. So it is displacement versus the distance from source. So when we draw a transverse wave, so we represent it as A, B, C, D. And AB are the crests and CD points are troughs. And above the line of disturbance, it is positive displacement. And below the line of disturbance, it is negative displacement. And along xy, the wave is traveling, which is distance from source. So basically what we are representing, the displacement versus the distance in case of transverse wave, wherein the crest region above the line of zero disturbance is a positive displacement we see, and below the line of disturbance we see negative displacement. So this is how the displacement versus distance graph for transverse wave is represented. So this is called displacement versus distance graph. So in case of longitudinal wave, it is density versus distance, and here also we can see the density is higher above the line of disturbance, that is zero disturbance, that is xy. So in this area we see more density and less density. That makes more sense. So this is more density and this is less density.